All right, it's time to start, right? Welcome all to this talk, and I hope you guys are enjoying Percona Live so far. I've seen amazing presentations yesterday and some today. So today's talk, we're going to talk about performance optimization. We're going to talk about indexes, but the main idea here is not to talk on how to create index or why we need to create index. So I guess we all know that we need to create indexes. Well, a bit about myself. My name is Charly Batista. I'm Brazilian, and I'm living in China for a long time now. And I'm also passionate about database. I've been working with database for a long time, including MySQL, Postgres, and other database. And this is something that I really enjoy to do. We can find me at my LinkedIn profile. It's here. You can also drop me an email if you want later. My email gonna be in the end of this presentation with my GitHub and also my LinkedIn profile. Our agenda today, what is this talk about? We're gonna have an introduction about the cluster and heap index, because we need to understand how they work on Postgres. Then we're gonna see some of index types, some access methods, and some overview in the end of this talk. What is this talk about? As the title says, this talk is about indexes, but we do not want to talk why we need to have indexes. But the main idea is how we can help the database to optimize or to use the index that we have on the best way. And to be able to do so, we need to understand how the database stores the index, how the database is organized internally, and how the database uses the index. That's going to be the main idea for this talk today. We are trying to understand how the database uses the index and how we can help our database to optimize that. This talk is main focus on Postgres and MySQL, but a lot of techniques that you're going to see here and the concepts that we're going to see here, they can be used for other databases as well. Well, let's start then. Heap or cluster. There are two main types of file organization when it comes to database. One of them is the heap file. This is the one that is used by Postgres, for example, and other database. We have some proprietary database in the market that they also use heap file. What is a heap file? The heap file is the simplest form or file organization that we have nowadays. As the name say, is just a heap of information on the file system. We can just use this as a comparison. So let's say we need to organize our books here. We can just put one after another one without any order, specific order. We don't care how they are organized. What we just need to know is the space that we have and if that book fits or not on that space. And this is basically what a heap file does. So all the data on the file system, they're organized in blocks. We cannot write a single byte to disk as a single byte to the database to the file system. That means that every time that we write or we read to the file system, to the disk, we need to read the block. So that's why all the files that you're gonna see here, they are organized in blocks. And the heap file is just an amount of blocks that are put one after another. So there is no order at all on the heap file. We cannot expect order. If you use a Postgres, for example, when we insert information on the table, the first time that we insert the information on the table, just because the file is empty, there is nothing there, the order that we're going to get is that insertion order. And it's pretty simple. We can get an example here. let's get started with some example. All right, let me just create one table here. Page table example. I'm gonna have an ID of integers, and that's it. That's a very simple table. So I just created this table, and I'm gonna insert into this table example few rows. Let's just insert 100 rows. Oh, if I do here, the order of this data inside of my table is just the order that we inserted here. If I do a select, start from example, so this is the order that I've just been inserted the rows. But what happens if I come here and delete from example? I'm gonna delete where ID is smaller than 10, for example. So I've just deleted 10 rows. If we select it here again, we don't have those 10 rows that we got. And if we insert those more 10 rows, let me start in 100 and insert. Well, may you guys guess where this data will be inserted? In the end, or in the beginning, or in the middle of the table? Well, this example here, let's just order. I don't want to put the order. Let's just select everything. Well, in this example here, they're going to be inserted in the end. If you go to the 100, we don't have the 100 then, since we didn't insert them. Of course, 100 to 110 doesn't generate anything, right? So they should be inserted in the end of our table. There we go, from 100 to 110. But what happens if, let's delete again. Before I delete, what happens if a process called out vacuum happens here on Postgres, on this table example? And, oops, on this table example, and just do some cleanup on this table. And then I insert again from 110 to 120. Oh, I got 20 rows inserted now. If I do a select, look, those are at the beginning of the file now. It happened just because when vacuum run here, it did a cleanup on this table. And why this happens here on this table? Why it needs to be clean? It needs to be clean because on a heap file, when a deleter, a row, a record, there is no real deletion in place. The rows, they are marked to be removed, but they are not really removed now. The space is not empty now. So we need a help from a process like out vacuum or vacuum that you just run on Postgres to remove and to make the space room for those rows that are coming out. And well, because of that, if I just remove something in the between, like how many rows I have here? Well, if I remove between a 75 and 90, for example, if I remove here, and then I insert again, from 130, 140. Let's put here to 200. Oh, if I insert here and if I select, we're going to see that our table from 75, well, I need to do a vacuum, right? Let's do a vacuum here. And let's again, 200 to 300. So we're going to see that our table from 75, it's going to be it's not a good mess. Oh my goodness. Yeah, that's a typo. Thanks, Marcelo. Oh yeah, my database is not that smart, you know. That's indeed. There we go. Now we got some room. And I'm gonna remove in the end as well. ID larger than 200 because, well, I don't want too many tables, right? So we have now a pre-empty table, so it goes to up to 200. That's fine. And if now we insert those here, so what's gonna happen is we finally should have from between 75. Look, we started 200 here from 75, and then we got back to 91. And then we go to the end, we start from 200 something. After 199, 200, well, I have a duplicated because it's not a primary, right? That's fine. So, but it jumps. As we can see here, there's no order at all. So we cannot expect any order on the heap file, even the insertion order, because we can make some space in between or in another place of the table, and then files can be inserted there. So we cannot expect any order at all on the heap table, on a heap file. And as I said, the delete, it doesn't remove. And for the same way, the update, it doesn't change in place. So when we do update a row, what it does, it marks that row as updated, as removed, and then it insert in the end of the table or in the next empty space. So, and because we cannot expect any order on the heap file, an insertion can be very efficient, because what an insertion does on heap file is just get the next empty space, or that can be in the end of the file, and insert there. It doesn't need to organize anything. And that's why a heap file is so efficient for insertion, and deletion, it's fine, like, and also an update, because it doesn't need to reorganize the file like we do for a clustered tables or clustered file, for example. Well, and this is the next one that we need to see, a clustered table. So a clustered table is a totally different type of file organization. It uses what we call a clustered index. So it gets one index, usually a B3 index in most of implementations, and it organizes the file on the B3 order. So it needs to have a key. That is the first thing that we need to understand when we work with cluster tables. So if we create a table using a cluster index, we should have a primary index. For example, InnoDB on MySQL, if we do not create a primary key on our tables, InnoDB gonna do it by itself. And it may sound something good, right? Because it will prevent that the tables to never have a primary key. So all the tables, they will always have a primary key, but it's not that efficient. It will have a index key that is used only to organize the table. But we cannot use that index to to select, we cannot use to sort. So in the end, instead of make things faster, they're gonna make things slower, because we have a table that has a primary key but cannot be used for anything other than just organize on the file system the rows. So, and this is what happens when we use a cluster index. So we do have an index, and all the index they have it's unique or primary key. So, and in the file system, the index, the rows, they're just stored on the index order. So it has another consequence. If we need to traverse the file, what it means, if we need to read the whole file, we cannot read the file in physical order when we have a cluster index, because we need to read the file in key order. When we traverse the file, we are just traversing a binary tree. And the problem is they are not sequentially on disk. So the B tree, when they're being stored on the disk, all those keys here, they're not necessarily stored one after another. They are not sequential. It means that we have a lot of random access to the disk. This is the first implication when we have a binary tree or a B tree on index. Not necessarily a binary tree, but a B tree on index. So we need to traverse the index in the key order. And key order is different from physical order. It means we have way more random access when we need to traverse a B tree, an index. So another implication when we use a cluster index is because of the index is the table itself, as we saw, the table is organized on the key order. Every secondary index, every other index that we create that are not the primary key, they carry on the primary key on itself. So if I have a primary key that is a large field, for example, if I use a varchar of 200, and my primary key is of 200 bytes, right, in most of platforms. So all the index that I'm going to create on this table, they will have the primary key and then the columns of the other indexes. So my index will start with at least 200 bytes in this example. And this can have a lot of penalty on the performance perspective and on the storage perspective as well. And that's why for databases like Postgres, or more specifically InnoDB, that uses cluster index, one of the recommendations is make your primary key as smaller as you can. So that's why a lot of DBAs or experts on the database, they recommend you just create an integer as a primary key. Create a sequence that is simple, it's small, and it keeps things organized. Well, from logical perspective, from application perspective, it's not always the best case. But if we care about performance, if we care about storage and cost, well, that's the thing that we should go for. And that is the reason, because when we use a cluster index, all secondary index, they carry on themselves the primary key. And we're going to see some implications in examples later. Well, we know that index makes things fast, right? So then let's make them. Let's create. It's SQL time. We want to, before we start creating the index, we want to know what type of index we can have on our database. I've been talking about this primary key, all those 2 slides before. And what is a primary? Actually, what is a primary key? What is the concept for primary key? A primary key, by definition, is an index that is unique and that identifies the row of the table. So if we have a table that has a primary key, that key can identify each of the rows uniquely. And theoretically, the primary key should be the best index that we can use to search, right? Well, not really. And I would say it depends. If we are using a cluster index like InnoDB, yeah, that's totally correct. If we search something based on the primary key, it's much faster than search from whatever others index. And the reason is, on cluster index like InnoDB, all secondary index, they have the primary key. So they have the address of the primary key. Then what they do, when we do a select on a secondary index, let's just do an example here. I have a few tables. Let me go to MySQL. Well, I have few tables here. One of them is this table with amp new. I mean, the name of the table is employee. How many employees that we have? Let me do a count here. Well, sometimes I hate this keyboard. Select count from employees. But I don't have the table employee because, yeah, of course, I'm on the wrong database. So let's use the correct database. And then now it should be, I still don't have. Yeah, I'm missing the count. Nice. It's like I don't know how to write a SQL anymore, right? Yeah. So I have here 300,000 rows. If I get whatever employee, select start from employee, where amp new, let's just guess one, but I hope we have this ID here. We don't have. I got one that we don't have. All right. Link 10. Well, if I get this ID here, it should be a really fast select, a really fast query, right? Because we are using the primary key. If I use Rick, an auto increment is not always optimal for many-to-many map. And well, I would say that it also depends. The key doesn't need necessarily mean to be auto increment, right? For example, this key here is using a logic behind of the key. What I meant to say is smaller keys, if they are faster to perform than larger keys. So if this example here, if I change this key, for example, instead of an integer to a varchar, so and I have a larger key, not because of the type, but because of the size of the key, and even if I keep the same order, the same numerical order here, when I search on the secondary index, I'm not talking about the primary index, but when I search on the secondary index, they will be more expensive because we need to carry on more information on the primary index. So what is the problem about having more larger keys on the primary index, or have larger keys at all? The problem is we always try to avoid access to the disk, right? Disk reads are expensive. And this is one of the things that we're going to comment and try to see here. That's one of the techniques. Disk reads are expensive. If I have a smaller key, let's say of 5 or 8 bytes here, I can put more rows in memory than if I have a larger key of 16 bytes. So I can have at least twice more rows in memory. So if I can have twice more rows in memory, when I do this select star here, it's going to put all my rows, but limit it to 1,000, right? So it's fine. I have enough memory here to put 1,000 rows on my buffer pool. But if I do not have, if I need to do another select in another table that needs this space here from the buffer pool, all this data here, they need to be removed for the buffer pool to make space. So then next time that I do this select again, that's going to be much slower because it's not on the buffer pool anymore. It needs to go to the disk. So, and this is the direct and first consequence of having larger keys, especially larger primary keys, because the secondary keys, they're going to be the size of all the rows that you have on the secondary keys plus the size of the primary keys, because they carry on the keys on the secondary keys. That's the main problem when we have a cluster index. That's why on most of the case, of course, there are situations that we can pay for the price, but for the most of the case, that extra price causes performance issues, performance degradation. And that is the main problem when we're talking about having larger keys or returning smaller keys. And as I said, on InnoDB, because they use the cluster index, the primary key, they also store it on the secondary keys, on the other keys. Well, other implementations that do not use a cluster index like Postgres, it doesn't really have the concept of a primary key. All the keys, all the indexes on Postgres and other database that implements heap tables, the keys are the same. When I say the keys are the same, I mean they have the same performance, the same type of access, they are stored on the same way, and the performance are the same. It doesn't matter if I search based on the primary key or if I search based on the secondary key. Because a primary key on Postgres is just a normal secondary key that is unique and not new. That's it. If I create whatever index that's unique and not new on Postgres, on the same type of data, they're gonna perform on the same way as any primary key on Postgres, just because how the heap table they do work. Well, we talked about secondary keys because of the main difference are what I just said. On cluster index, they carry on the primary key, so we need to be careful of that. And on Postgres, they are all the same. Basically, Postgres only have secondary index. Postgres doesn't have the concept of primary index on its table. And another thing that we can create, or the type of index that we can create, are the multi-column index. Well, as I have an example in my example here, I've created an index on this table here that is, I have 4 columns here. It's already there. So I can make a select here using this index. For example, if I use Mary, for example, here, I'm gonna use the index and will make my select quite fast. And if I use Mary, and let me remove this like here, equals, and get whatever name. returns immediately, as we see. However, if I do not use the index, let's say just use this here, it may take some time. It took a bit more time that when we used the index. So the thing about creating composite index is we need to understand how they access the data. All the composite index, they need to access the columns from the leftmost. What it means? It means that in my example here, I created the index using the columns first name, last name, and birth date. So last name it's on my index, right? If I use here the last name, it should use the index. What if I explain here the select? What it says? Well, it says that it may have an index. You know, it may be possible to use an index. And in this case, actually, it did use an index. And we will understand why Postgres, I mean MySQL, in some case can use index like this one. But let's get a bit worse. Before I need to get the without explain. All right. Let's explain this one here. Right here. So what happens when we have a composite index here, as I'm trying to explain? Because how the index is created in MySQL that is using a B-tree and on Postgres as well when we're creating the main type, the key, it needs to be accessed first from the leftmost row here. So look at how many rows the database needs to read here to be able to try to use this index. So if we do not start, this is what I want to say here. Exactly, the result is the same. We read all the rows. If we do not start here from the index to search the first column, the database is not able to use this index. Sometimes it can do some optimization that we're going to see later here that MySQL tried to use. For example, ICP, that index pushdown. So it tries to use the index even if it's not totally possible to use the index. But when it sees like, okay, I see there is an index on this column here, and I may be able to use this index. So if I go to the index, even though it's not the best alternative, I can avoid some access to the table. This is what we call index condition pushdown. The database tries to use the index even though it's not totally possible to use the index. But most of the case, what the database is going to do is just ignore the index that we have here, because we need to always start from the leftmost column, the column that when we created the index was from the left. So if I start here with name equals, let's just copy one name here, Zorka. And if we explain now, I need to put an end. And if we explain here now, we can see the huge difference. Look how many rows the database needed to read just to get this information. And compare from the other one, when it says, okay, I might be able to use an index here. This is the size of the index, but I'm not going to use this index. I'm going to ignore this index. Because, well, it's not optimal, it's not efficient. I need to read too many things to be able to use this index. Here, the database was clear. Well, look, there is no possible index that can be used here in this situation. And we understand why the database sometimes even consider to use the index, and sometimes it just ignore it all. And this is one optimization that we can do manually. To be able to use the composite index, we need to always use the leftmost column. In this case here, my index has first name, last name, and birthday. So it's only using the first name. And how I can tell that it's only using the first name? Because of the k-length. If I put a last name, let me just select someone that has a last name. So if I put here last name equals, where's my last name? This is the last name. I'm going to stop just by here. Let's compare the k-length. And the first execution that I said that was using only the first name, this is the k-length of the index that it used to search. Look, the size is 16. Now, when I add the next one in the row, that is the last name, it increases it to 34. If I ask him to also add the birth date, it uses the other index as well. And also, these are what is using to compare the index. What is the type of reference to access that index? Here, we only have one row, one column of the index being used. So it's passing one value to that index to be compared. And that value that is being compared is constant value. It's just something that we put here. It doesn't change. It's not getting the value for any other select or join. It's constant. So, and then when we use the two columns from this index, so it's, yes, also using the constant value for each of the columns. And then here we have the same. We are using the tree to fetch the information. And if I just remove here, even though I'm using the last name and birthday, so yeah, it doesn't use the index at all. And this is what we get here. So we need to be careful when we use composite indexes on any database. And this works for the same way for MySQL, for Postgres, and for the majority of the databases. And one thing that I told you, that I said that some database, for example, MySQL has, that can help the index is the index condition pushdown. So what is an index condition pushdown? The database sees that there is an index, and it may be possible to use that index to optimize the search. For example, here, let me just do a cleanup here. I want to show. Okay, I'm gonna do a cleanup here. I'm gonna disable the index condition pushdown here, optimization, because my database is used by default. So I'm gonna do this select. We'll see that, well, it's not bad, right? It's pretty fast. It's still 0.007 seconds. I'm gonna enable the index condition pushdown, and we probably don't see much of difference here. Well, we saw. Because sometimes, because I just have just a small piece amount of data here, the difference is not that clear. But look, the difference here. we went from 0.007 seconds to 0.02. It's even nicer if we check the profiler here. This is the time that took from the database to do without the index condition pushdown. And this is the time when the database used the optimization, the index condition pushdown. So in some case, we can get a huge performance improvement, because what the index condition pushdown does, it sees that it exists an index, and it may be able to use that index. So it goes to when I do the select here, it goes to the first name, Mary, and finds that on the index, all the information. Instead of going to the table and fetch all the rows that has Mary, like this would be what it would do, it would go to the table and fetch all the rows that has the first name like Mary, and with this information in memory, it would apply this filter here, because this filter, as we can see, the percentage on the end here, the predicate, doesn't allow us to use a B-tree index. So it cannot use this for the index. What it would do is, it will get all the Marys from the table, from the index. Then with that information, you get the primary key, would go on the table and fetch. This would be fetched from the table, put on memory. And then from this table on memory, it will apply the second filter. We needed to read from the disk 224 rows. When it uses the index condition pushdown, it works differently. It goes to memory to get the index with the it's being used, so it gets all the Marys from the index. And with that information in memory from the index, it applies the second filter. And after applying the second filter, it goes to the table with the information that it got. So the main difference is the time that the database accesses the table. Without index condition pushdown, it accesses the table after when it gets the information from the index, the Mary. When we use index condition pushdown, it accesses the table after applying the possible other filter that exists on that index. So we read way less data from the disk. And because we're reading less data from the disk, the access time is much faster. And this is what this optimization does. And we'll see here that we can use this optimization. So what are the index types that we have? Well, it will highly depends on the database. The majority of the database, for example, Postgres and MySQL, they have at least in common B-tree index and hash index. B-tree index is the most general index that we can use. So if we are doing search or selects using a range scan, that is most of the case we are using range scan. This is one of the best index that we can use. That is the B-tree index. And that's why it's usually the default index for most of the database. When you create an index with the database, you just create it as default as B-tree. The hash index, it's also common, is, if I'm not mistaken, all the database, they also have the implementation, at least the ones that I know. They do an implementation for the hash index. A hash index, it's a very efficient index when we have an equality, when it's not a range scan. Hash index, they don't work for range scan, because how a hash works? Well, we give the database a value, and it uses an algorithm to calculate that hash and create a table with those hashes. It's like if I do a select MD5 here, for example, Charly. Oops, I need to. Oh, this is one hash, right? So this is not exactly what the algorithm, the database uses, but the idea is the same. So whenever I create a hash index and I insert a Charly on that table, it will get this value of Charly, and we calculate a hash. and we use that as a position on my index. So then it will have always the same position. When I search, every time that I use the same algorithm for the same input, it will generate the same result. So the time access for a hash index is just time equals 1, because it theoretically has only one position on my index, and that position is fixed, it won't change. And every time that I need to access this information, I can access the very same position. And that's why a hash index cannot be used for a range scan, because I only can do an equality, because it will always give me this same information. And because if a hash, it cannot be, we can only order by position. We cannot create a tree as we do for another index. And most of the database, they do the implementation. And there is a problem with the hash index, what we call collisions. The algorithm for the hash, for the index to be efficient, it needs to run really fast. And for a hash to be fast, it needs to do less operation, right? To use less CPU. So the risk that we have different inputs, for example, if I put here Charly, I won't get a collision here, but if just an example. So a collision is if I use Charly and then use Joe. If the hash, they were exactly the same values, that's not this case here, but if they were exactly the same values, then I have a collision. So because of collision can happen, we need to have a way to find out, right? So if the algorithm that I use, it causes a lot of collision, then my index is gonna be less efficient. For the other hand, if I use an algorithm that causes less collision, then it takes too much time to calculate. And when I'm updating the index, it can be very expensive. So usually an alternative is use a fast algorithm that can cause collision. And when we have a collision there, we just store that position. And on that position, it points to another index. That can be a B3 index or whatever other type of index that can be organized. So then we can still use a hash and be efficient. Other types of index that we have are the gist index, for example, on Postgres, and block range or generalized social trees. Most of those generalized index on Postgres and the implementation in other database, they work with what we call the inverted index. So they're basically a B3, but how they organize is in the order they organize. It's different. So and they are very efficient when we have, for example, an index that has a lot of values that we have a repetition for a lot of values. That when we do not have uniqueness that is pretty high. So, for example, if I have a column that is sex, so, or if I have a column that is gender, let's say, put on this way. So we don't have many values for gender, right? And what an inverted index it would do, instead of create a huge index, a huge tree that for each row we have one entry in the index, and we have a lot of repetition for those values, it will create a small tree with those values. It will just use the unique values. Let's say we have gender, and we have 5 values on the gender. So it will have a tree of 5 values. And then inside of those, they have pointers for those rows that are of those values. So when we search, we do a search for, let's say, gender equal a man. instead of go to traverse the index for 1,000 rows and just to figure out which are the demands, it can go to the index and just have one single entry for the index that points to all the rows, that has a pointer for each of the rows in the table that has that gender. So it will be very efficient to search all the employees that have that gender, for example, because it doesn't need to traverse that whole table. So the access time is very efficient, especially when we have those columns that they use a lot of repetitive values. Those are the inverted index. Well, MySQL, they start doing implementation on 8, but they still young age. And Postgres, they implement since long ago, since version 9, 8, I don't recall on top of my mind what the version that they start implementation. Well, on having that in mind, then we need to understand how the tables, they can be accessed. We have basically 3 types of access on the table. We have the table scan. This is when we need to traverse the whole table. Yes, inverted index, they are usually present on full text index. And that's the main idea for the full text index, because we have a lot of repetition on the text. Let's say on this text here, I have needs to traverse the primary index key. And look, I have order, order, and order, order. All those are repetition. If we just create a normal B3 index, we would have a huge index with all those repetitive words here. On the full text index, when they use inverted index, they get this order here, and they put it on the index. We have only one entry for this word order in the index. And that entry will point for the position or the IDs on the table that we have. That's why it's called inverted index, because instead of we have the position on the for every entry in the index, we have the order itself. I mean the word itself, and then it points. So it has the pointers on the values of the index. That's why it's so efficient for full text. Back here to the table scan. And so a table scan is just go to the table and read the table. That's it. It's the very simple way to read line. We just go and read the whole table. As I've explained before, InnoDB is not efficient doing table scan because it uses a clustered index. It needs to access the table in index order. So it generates a lot of random reads from the table. Postgres is less inefficient. It's not that it's efficient to do a table scan, but it's less inefficient because it accesses the table in physical order, because it doesn't need to organize, order anything. It's just go to the disk and read the whole table in physical order, and that's it. That's what it does. So for table scan, when we have a non-clustered index, it's more efficient to have a cluster index from the access. Another type of access that we have is the index scan. Here on the index scan, using a cluster index is usually more efficient than a non-cluster index. So because the cluster, especially when we're using the primary key, or using a primary key on the cluster index is the most efficient way to traverse and to access the table. There is no other way that is so efficient, because, well, the primary key has the rows itself, has all the values that we need to traverse the table. So it's really efficient to traverse the index on primary key order. And the Postgres, for the other side, is not that efficient, because on Postgres, when we traverse and we use the index access, we need to go to the index table first, the index file. We'll read the whole index file. And for each entry on the index file, on the primary index file, we need to go to the table and find that row and read. So we have a lot of random access now, because we need to traverse the B3 index on one side, and from the B3 index, we need to go to the table. So we generate random access on the index and we generate random access on the table, because now we are traversing the table on Postgres using the index order that we just got. So it's less efficient than traverse use on the when we have a cluster index. Another alternative is when we have just an index scan. Sometimes we can create an index that has all the columns that we need for the select. So we don't need to go to the table at all. We only need to traverse the index. This is the best, the most optimal way to traverse, to read, to access the table. This is called full index scan or only index scan. And some authors, they give different names. Or covered index, that is a common word in MySQL world. So when you only need to read the index. So you just go to the index, get whatever you need, and then you come to the table and you get the information there. So having that in mind, well, yeah, this is the index only scan, what we just said. Having that in mind, we can help our database with some techniques to improve the performance. The first thing is good statistics. All the databases, when I mean all, literally all the databases, they use statistics to decide if they are going to access the index or not. If we have bad statistics, the database can pick the wrong index or can even avoid choosing an index at all. So keeping the statistics up to date on the database is one of the best techniques and the best way to make the usage of the index efficient. Another one is what I just call it here, the covered index. And this is what makes this select here so interesting. Let me, where are my selects? And all right, we're here. So remember that I said that the database here, it is even considering to use that index to access the data, right? Even though it cannot access this index directly here, because this is the last row from our index here, the database is even thinking about to access that index. And it said, look, it's possible. I even say know what is the k length here for this index. And the answer is because it's using an covered index. All the rows that I need for this select, I can find in this index. But you can think about, well, look, I have 1, 2, 3, 4 rows here, right? 4 rows. Let me just put in the order of the index. Oh, I have 4 rows. And my index was created with only 3 rows. Well, how is it possible to have 4 rows? It's possible in MySQL because I also selecting the primary key. Remember, the primary key is inside of all of the rows that we have. So, and that's why it can even think about access this index here, because, well, it doesn't need to go to the table, even though it's not so efficient to use the index to access. The index is still smaller than the table. When I go to the disk, I read way less data from the index than to the table. But what happens if we use the first name? I have a first name here. Well, if we use the first name and we make this index efficient, the database will do what it calls index-only scan. So this is the covered index. It can really use the index to get all the data in the index order. The first one here is using the index, but it's not using the index on the index order. It's using not in the key order. It needs to traverse the whole index. Here, it doesn't need to traverse the whole index. It can filter. It said, look, I only need like that few rows. I don't need to traverse everything. And if we do the select, well, it doesn't find anything from Mary. Let's do the select here without the explain. So if we do the select, it's pretty fast. It's pretty efficient because everything is coming from the index. This is one alternative that we can use to help the database. So, and we can use this strategy to go even further. Let's say here, I have this table here in another database. So this table is a pretty large table, but like if I do the select here, well, it's pretty fast, right? I'm getting 10 rows from the beginning of the table. That's it. However, if I go a bit further, if I get the same 10 rows, but like later on from the table, it can take way more time because it needs to go to the table. And remember that I said the accessing the table is inefficient. It needs to go to the table, read row by row, and after read those 90,000 rows, it will do what I want it to do. That is just get the length of this column here. So how can we use this index-only access to optimize this one here? Let's try to do it now. So I'm gonna get the lookup L. I'm gonna do a join here with the same table lookup on L1. So, but what I'm gonna use here is, well, first of all, let's check the table lookup. What we have here. Show create table lookup. Okay, I want to see. Well, we have a primary key index here. That is in the column valid. So I'm gonna do an L.value equals L1.value, right? And then order by L.value. And here I'm gonna do this L1. Well, what I just did here is I'm trying to select only the rows from L1. That's why I'm doing the offset here. And then using this offset here, I'm applying whatever I need to apply here, right? So L.value, all right. And let's explain this here. Oh, I forgot, we don't have an index here, right? Well, if I want to use the index scan, we need to create an index here. So alter table lookup add index ADX lookup on this column here. Hope you still remember how to alter table. All right, I need to say what is the size. Let's do something different. For now, where L.id select column that we have here. Yeah, it's IT. Select ID on. We're forcing here because I don't want to create MySQL has size limits when we create an index on B2 index. Because this is a text, the limit it's larger than the size limits of the index. So I want to keep calculating using everything that we have here, but it's not for in the index. But I still want to use the index access here. That's what we do here. If we do deselect here, IT, do deselect here. So if we do deselect here, see how much faster it is. From 200 seconds to milliseconds to few milliseconds. And then we can use the ID that is just the index, the primary index that we have, to fetch the rows. So this is the same as we're doing. Oh, yeah, I don't have L1 here. This is the same as we can do the join. If we had the index in this column here, that we would be way more efficient. Look up. Oh, nice, MySQL. My version doesn't, yep. MySQL couldn't do this. What we're trying to do this here, what is the major problem here? Okay, let me come back to the original select. So what we do here, what we're doing here, we are forcing MySQL to use this index access here. Well, actually, if we know the IDs, we can force MySQL. But look what I'm doing here. I'm doing full table scan. I'm doing just the select without any where clause. That's the problem. Let me just get here the ID, and that's where we're gonna understand what is the main problem here. Right? Let me get the original query and put the order by and here. So it doesn't know who is L1. That's correct. Oh, this is the problem. MySQL doesn't know what we want, what we need. If I tell MySQL that I need, for example, let's put the size of the limit here doesn't matter. What really matters here is the offset. Look, even though I'm just selecting one row, see, the time that was selecting the 10 rows, they're mainly the same. Sometimes it can be even worse because now MySQL needs to do more work to clean up the results. Because it just dropping all the rows, it just then get one rows. So why MySQL cannot do what we are trying to do here automatically? Because MySQL doesn't know what we want to do. We're telling him, select everything from this row. After you select everything from this row, just drop all of rows, the millions rows, and give me one row. This is an example that is it's very common. We may think, well, man, it's a stupid example, right? But every time that you go to a website and you need to paginate that website, you need to do this. You need at least to do a select count, and then from the row number 1 to the row number, and paginate. This is a very common example. And there's a lot other examples that we can use. However, if we tell MySQL, I want only the ID equals, this is the ID number, right? So I don't need to do an offset because it's only gonna return one ID. And this is the access time. It's 140 times faster than accessing this one. Because now we are telling to the database, I want exactly this row. And this row has an index. So the database can go to this one and get an index, and that's it. And that's why it's so fast. And that's why we should try to always avoid rows scan on MySQL, on the database. And if we remove this, we do an explain here. Explain will tell us what is going on. Of course. Explain will tell us. So explain will say, man, we are accessing this table. I know we are just accessing this table. I maybe use an index to access this table. It may be possible to use an index. You know? Well, maybe I can. It didn't even know which key, which index it will try to use to access. But eventually it found out, okay, I can use this, that is my primary key. I can use these keys to access this index. This is the size, it's an integer, has 4 byte size. To roll this, to read this. But look, I need to read 90,000 rows. I'm gonna fetch 90,000 rows from the disk. I'm gonna put all of those rows in memory, and just to clean up for you to get one row. And that's why MySQL cannot do it, not only MySQL, but any database. They cannot do it automatically. They cannot do it by ourselves. So, however, if let's explain this one. All right. It's ambiguous because this should be L1. All right. And look here, the table L, now it knows, well, I can use just this index. I'm gonna do a lookup on this index, right? I'm gonna read, look that here, it didn't even know that it was possible to use the index. It's gonna do, look, I'm gonna do a lookup on this index. From this index only, I don't need to access the table, but from this index only, I'm gonna read 9,000 rows. And then I'm gonna get exactly what you need, that is the primary key, and then I'm gonna get one row. Yeah, they explain they are based on statistics. They don't give really exact numbers. So when we do an explain, this is the estimation. The database is estimating. Look, I believe I'm gonna need to access 9,000, 9,001. 9,100. That's why I said that we need to, we have good statistics. Because if we have bad statistics, the database will think, well, I'm asking 90,000 rows, right? The database will think, well, man, I need to read 300,000 rows to get this 90,000. It doesn't make sense to go to the index if the table has 400,000. It's much better just go to the table. And then, just because we have wrong or bad statistics, the database will avoid going to the index and do a full table scan. And then we are doomed. And yeah, that is how we can try to help the database. We can give them the path that we want it to run. So look, I want you to use this index to get all those rows, okay? After you get all those rows, you're gonna get one of these rows. Go to this other table that's actually this very same table. Get me, can be even better. Get me the ID that I want. In this case is the primary key. Get me the ID here, and just get from it. Give me the row that I need. So that's going to be really fast. If we do the select here, this is what we get. So this is one of the way that we can have to help the database without changing anything, without creating a new index, without dropping index, or without redesigning the database. So when we know that we already have those index, or we see some queries that they are performing really bad, so we can just help the database and avoiding random access to the table. Yeah, that's why I said here we need to create the index here. That's why we created the other subquery, right? Remember, the problem is we don't have this index here. So we need to get the same select here. Select. MySQL won't let me do this because this version that I have here doesn't have subquery with image, right? All right, let's select. What is the? Let's do this here. So this string. Let's change our table, right? Let's do this. Don't look up. Let me just make sure this works. Substring. This needs to be a varchar. So this string. I want to select one from. Right. This is what we get here. I'm going to alter the table lookup. Alter table lookup. Add column new. That is going to be varchar of 100. That's what we want. And is this not new? Yeah, not new. Right? So we alter the table. And we're going to do update table this. Lookup set new equals the same substring, right? MySQL, we will already work just in the index to identify. Well, not really. Any database, including MySQL, it's I mean, the optimizer for MySQL, not any, but for the most of databases, they are cost-based. What the optimizer is going to do? They just check the cost, if it's effective or not to choose that index. And we can try to do, let me see if my database here has this option. Okay, while it does that, oops, I don't have. Let me just cancel here and use test. Oh, we can ask the database what it's doing, right? So I can go here to tell to the database, look, I want to trace exactly what we are doing. It will tell us what the optimize is doing here. Let's enable this profile as well. All right. What I want to do is let's execute this one here. I don't want this. So let's just see what the database is doing. And I want to ask the database to get me the profile. This is exactly what the optimizer tried to do. I'll copy here. Let's copy here. And here is better to read. So this is what the optimizer did. This is the optimizer's work. So it will get the select, it will split the select, and for MySQL, everything is a join in MySQL. It will tell us, look, I'm doing a lot of joins. Even though if we have only one select, it will call a join. Every table internally is working like as a join. So, and then MySQL is, you check, well, let me check if there are any where clause. It will check the where conditions. We have the where conditions here because we have the join. So it will get everything from the join, from that join that we did, and it will transform in where conditions. From the left side, we have the table that is accepting, and from the right side is the first table that's been selected. And the access type is not the type of constant now. It's not a constant access because it's changed based on the table that it's just reading, right? So we are reading a lot of rows from the first table, and then it's changing the value to pass to the left side of the select. So it got all the types. So see, we have an equality. It checks if can do a constant propagation. It means if the value are constant from one side to another. For maybe it's a multiple equal. So it may be constant or not, but we have multiple times because, as I said, the table has been reading many times. So after that, it will check what if the tables that we use and what are the costs. Well, if I do a table scan from this table lookup, the first table with the L, when we name it to the L, we gave him. This is the how many rows the table has, and this is the cost to access that rows. This information is based on the statistics. It may be or may not be correct. So, but from the statistics that they see, look, I have this many tables, and this is the cost. And then it will check, okay, can I have other different types of plans because I have the full table, the access table, the scan table, so I can access from the database. I maybe have indexes. Well, yeah, I do have indexes. Well, let's see how expensive are those indexes. Well, if I get this index here, this is the many rows I will have here. I have more than 1 million rows. And this is the cost. Is the cost of accessing to the index cheaper than the cost accessing to the table? Well, in this very specific case, yes, the cost is cheaper. So let's choose this access. And well, because he's choose this access type that's referenced using the index, the other access type that was a scan, it was not chosen, so chosen false. And the cause because it was not chosen is because the cost is too high. It's not cost effective. And in this very example here, it chose to use the index not because the index exists, even though it's a primary key. It chose to use the index just because it's cheaper to use the index. Let's try to do something different. Instead of this select here, let me count how many rows we have. And let's get the very end of the table, right? Select count, start from lookup. All right. Want the, I don't know, 2, 3, 1, 2. This is what we want, right? Let's do the select. A bit more. Let's again get the all right, it's not here. Let's get my notes. Hit this format. So if you get here, let's see what is the cost for this one. Let's go. In this case, we still get the cost is cheaper. The optimizer still believe it's cheaper to go to the index than go to the table. But again, having an access, if we just go for the select the whole table instead of we can get just a larger cost. And that's why the optimizer choose to use an index or not. It's not because it's a primary key. It's not because it has less role, but because the cost that it gets to access to that index. Just because we're getting that row, and this table is a pretty small table, and that's why it influenced that the cost of the access is so small. Because if we had a larger table, the cost would be, larger table with more columns, the cost would be much larger. And that's why it's so, the database, we cannot just tell that, okay, the database will always access this using the index. That's not true. Having an index or having a primary index doesn't mean that that table, even though it's usually the most efficient way to access the table using the primary index, it doesn't mean that it will always use that primary index. The database will check the cost. If I have good statistics, I sort of have, see, the database, on the database statistics, it's just found that the table has 94,000 rows. Actually, it does have 100,000 rows. Maybe if I update the statistics, those costs gonna change. And that's why when we have this access here, it's not so efficient because, well, I don't have an index on this column here. If I had an index on this column here, and we do the explan, if I had an index on this column here, it wouldn't need to do a file sort. It wouldn't need to access the table at all. All of them could be avoided. All of them could be solved in a better way. It could use the index to grab the information and doesn't need to go to the table. And this random access on the table, that when it uses the index, it needs to get the key number 1. Okay, key number 1 is where in the file system or in the position X. Key number 2 and another position, maybe in the same, but maybe not, because they are not stored in sequential order. They're stored in queue order inside of the disk. So maybe what it seems to be in the index ID, a row that is on the same page, when we go to the table, it's in totally different page than the just previous ID. And that's why the database uses cost, because this random access on the disk, it has a cost. And sometimes it's make the index inefficient and very expensive. And it's cheaper, it's much better. I just do a full table scan, then go to the index, and then come to the table and go to the index again and come to the table and just pick in random values on the disk, and that is causing the cost. Well, I hope that answered the questions. Yeah, we are way after the time. And that's it. The summary here is, well, UniDB use cluster index, and sometimes it's not that cheap to use the index. So accessing using the primary key is always efficient, is the most efficient on UniDB. Postgres doesn't have a cluster index, so all the indexes are the same, all have the same type of access. I mean, all types of the same index. If we have a B3 index that is primary key and a B3 index that's not a primary key, they're going to work on the same in Postgres. Of course, B3 index and GIST index that use a inverted index, they're going to have different access time and different access type. And the index performance, it can be improved or it can be reduced, depends on how we use our database, our queries. And you can help the database to improve the query performance. Well, that's it, guys. Thanks for your time. I hope that was valuable. And, well, just one more thing here. Let me put... This is my email. I said that I would put here and I forgot. So you can find me here on my LinkedIn profile. You can also find me on my email. And both this presentation and all the text files here that we used from this presentation would be on my LinkedIn. Thanks for your time. And I hope you've enjoyed and learned something on this presentation today. Thank you and have a great day.